The Unit 2, Introduction to Fracture Mechanics of the mentorship program, will cover the following subtopics, starting with Introduction, Fracture Mechanics, Stress Intensity Factor, Crack Tip Plasticity, Fracture Toughness, and R-curve. We have already covered the introduction part. Today, we'll see the fracture mechanics. The Inglis has found the solution of a plate containing circular hole, and the relevance of all the solution is not applicable to the fracture for this. For the fact that if you consider a plate which is subjected to remotely applied stress sigma at far field plate, and if it is in equilibrium, so obviously the stresses at any point will be equal to sigma. Once you have a discontinuity in the form of hole, since still it is in equilibrium, the stresses has to pass through along the hole, thereby it reduces stress concentration at point A and B, where it is given by sigma max by sigma y equal to 3. That is for infinite plate with circular hole, will have a ket equal to 3. Now, if you consider the discontinuity in the form of ellipse with the major axis of 2a and 2b, then stress concentration factor is given by 1 plus 2a by b, or 1 plus 2 square root a by rho. Rho is the radius of curvature. So one can imagine the crack by collapsing the ellipse minor axis 2b equal to 0. And in that case, we'll find that either radius of curvature is to 0 or b is equal to 0, then your stress concentration factor tends to be infinity, for which is not theoretically possible to have a structure stress concentration having infinity. So that's why it's not able to explain the stress distribution either the crack tip or stress concentration factor cannot be used to characterize the stresses at the crack tip. So the fracture mechanics started with the Griffith theory, who was studying, working as a scientist in Royal Aeronautical Society. And he was doing research on how to prevent failure of the windshield. And so he started doing some experiments in way back 1920. He was doing an experiment by taking a glass rod and breaking into two to see what is the load it takes for failure. Then on the basis of energy balance analysis, he was considered the weakening effect of cracks of the strength of brittle materials like glass and derived relations between the crack size and fracture strength. Griffith's classical work on fracture of brittle material like glass represented the beginning of fracture mechanics. So how it all started, because he was wondering that the strength of brittle metals like glass fell short of the theoretical levels of strength despite great care in maintaining specimen proportion on an optical scale. So if the material were to fail or fracture at the theoretical strength, the applied stress would also reach a maximum, and the atoms on all planes normal to the applied stress will be pulled apart to position corresponding to the maximum in the interatomic force curve. This should mean that fractures should occur on all parallel planes normal to applied stress. This doesn't correspond to the way brittle material like glass fractures. On the other hand, fracture occurs on a well-defined plane. Hence, Griffith postulated that a typical brittle solid must contain sub-microscopic cracks or flaws on a microscale, which weakens the material, thus preventing it from achieving theoretical strength. So, in the basis of his study, he come out the relationship between the stress, applied stress with the square root of damage as a constant, which is given by square root of 2 E gamma S by pi, where sigma is the applied stress, E is the Young's modulus, and gamma is the surface energy density. So obviously, if the damage is small, we need a larger stress to fail it, or if the damage is more, you need a smaller stress to fail. So that's what the product remains always constant. So Griffith obtained a fundamental relationship between the crack length and the applied stress sigma, with which the crack is in equilibrium. If the equilibrium is unstable, this condition governs fracture due to unstable catastrophic crack extension. So Griffith proposed that an existing crack will propagate when the released elastic strain energy is at least equal to the energy required to create a new crack surfaces. So to prove his theory, he determined the surface energy of the glass in the liquid form. And surface energy, nothing but is related to the surface tension. So he verified the theory with a crack did experiment with the glass. So he determined surface energy density gamma s by measuring surface tension of glass in liquid state at different temperature and extrapolating the same to room temperature. So thus Griffith determined the right-hand side of this relationship and determined fracture strength as a function of crack length. The experiment results agreed well with the prediction with 5%. So the relation, what it says, as the crack length increases, you need a lesser stress to fail. And if it is crack length is small, we need large stress to fail. And obviously, numerator values are all constant. So thank you.